Hello Physics Nation, my name is Nate Larmond and I'd like to do a Khan Academy problem on a diagonally launched projectile. The key to understanding diagonally launched projectiles is freezing the action at the moment of launch and imagining the velocity of the projectile as the hypotenuse of a right triangle. So, we were breaking up displacement vectors like northeast into its northern component and its eastern component last week. And the cool thing about vectors is the math is exactly the same, whether it's a velocity right triangle or a force right triangle or an electric field right triangle. The mathematics that describes, this sort of stuff, trigonometry and Pythagorean theorem and all that, is the same. So this week we're going to talk about velocity right triangles. So like I said, you just picture the initial moment of launch and its motion as this hypotenuse of a right triangle, and we're going to split it up into its horizontal and its vertical component. So sooner or later you're just going to memorize hypotenuse times cosine of theta is the adjacent leg. Okay, so in this case the initial horizontal velocity is the launch velocity multiplied by cosine of theta. Well, that's because cosine of theta is this ratio, the adjacent leg divided by the hypotenuse. And the trick we do over and over again is just to substitute in the physics quantity, this time, for the math quantity. So they call this the adjacent leg, and in this scenario, that's the initial horizontal velocity. Okay, so adjacent becomes Vix, and the hypotenuse becomes the initial velocity, how fast it's moving at the moment of launch. And all you do is multiply both sides by the hypotenuse, or the initial velocity, and it comes over here. All right, so same deal in the y direction. The initial vertical velocity is just the initial launch velocity multiplied by sine of theta. Why? Well, because this is the definition of sine of theta. It's the ratio of this leg opposite to this leg, hypotenuse. And again, we just replace the initial vertical velocity with opposite and the initial velocity with hypotenuse. Multiply both sides by the initial velocity, and there you go. And you will memorize these sort of pre-packaged formulas. They're useful. Hypotenuse sine of theta is the y component. Hypotenuse cosine of theta is the x component. Pardon my scrolling. Once you split the motion into horizontal and vertical, then it's just kinematics time, except in the horizontal direction, it's really simple kinematics. This VI cosine of theta is equal to the horizontal displacement divided by the flight time. And that's it, because there's no net horizontal force. Gravity is down, and that is totally independent from the horizontal motion. And therefore, there's no horizontal acceleration. Okay, so force and acceleration are proportional. That's, the conversation we're about to have. Newton's laws describes how force and mass affect acceleration. And vertically, we have, like I said, one force, the only force that acts on a projectile, the object's weight, or the force due to gravity. And I tried to squeeze in all of my kinematics equations. I got a little sloppy here, I apologize. So the average vertical velocity equals the vertical displacement divided by the flight time. The average vertical velocity also equals VI plus VF divided by 2. And then we have the two fancy kinematics equations. Displacement equals 1/2 AT squared plus VIT. And Vf squared minus Vi squared equals 2a delta y in this case. This is vertical acceleration, initial vertical velocity, final vertical velocity. You could put a little y subscript on all these guys, except for time, obviously, that's a scalar. And then the definition of acceleration, a equals Vf minus Vi divided by elapsed time. This is a very famous acceleration, negative 9.8 meters per second squared. So famous, it gets its own variable, g. And thanks for watching. See you in the next video.